So in the last video, we talked about how do we add a new node to a binary search tree. And today we're going to be talking about removing a node from a binary search tree. So remember that a binary search tree is a binary tree such that all of the values in the tree that have values less than the current node are going to be on the left, and all of the values in the tree that have a value greater than the current node are to the right, assuming that they're in the subtree, right? If a value is in the subtree and it's smaller, it's going to be on the left. If it's in the subtree and it's greater, it's going to be on the right, right? And we talked about searching in a couple videos. Basically, the idea is that as we search, we start at the node, and we use that property that smaller things are on the left, bigger things are on the right, to help us search through the tree. So here we're searching for 7, we start at 8, and we know that 7 is smaller than 8, so we have to go to the left, and it's larger than 3, so we have to go to the right, and we find the node that we're looking for, right? And when inserting, we do something very similar. So basically, we start at the root. So here we're trying to insert 13. We start at the root, and we know that if it's bigger, it must go in the subtree on the right. If it's smaller, it must go in the subtree on the right, on the left. And basically, what happens is at each node, if it doesn't match, so if it matches, we don't insert it again, right? But if it doesn't match, we recurse to the right subtree if it exists, and so on until we get to a point where we try and recurse to the left or the right, and that pointer is null. In that case, we can insert our new node in that location. So inserting in this way always keeps the binary search tree properties, right? It keeps it so that if you're searching for 13, we can always take this path and you'll find the node that you're looking for. Removing is a little bit more complicated because, again, we need to keep this property together. So there's 3 basic situations that happen when you're trying to remove a node. So we'll go through each of those as an example, and then we'll talk about this actually implementing it in class. So the first one, so say we're trying to remove 2 here, So the first thing is always to find the node to be removed, right? So we traverse through, and we find the node, and it turns out it's a leaf, right? Well, if it's a leaf, we can remove it, right? Boop, it's gone, and this is still a binary search tree, right? Because it was a leaf, it didn't have any dependents, right? So you don't have any trouble just removing it, and there's no consequences. So another situation is a node that only has 1 child. So here, if we wanted to remove 3, we search for 3, right? We find 3. Well, here our instructions say just to replace it with the child. So we get rid of 3, and then we move 7 into that spot. And again, you can see that our tree is still a binary search tree. If you're looking for 7, it's to the left. Anything else is to the right, because everything else is bigger. So the real complication comes when you're trying to remove something that has 2 children. So here, if we wanted to remove 8, right? We want to remove 8. Well, it clearly has 2 children, so we can't just remove it. Otherwise, we wouldn't have a root anymore, right? So what we want to do is we want to first, it says find the smallest value in the right subtree. Smallest value in the right subtree. So we start in the right subtree at 15, and we recurse always to the left until we reach a null pointer, right? So here we go from 15, and we take its left pointer, and we end up at 12. If 12 had a left child, we would keep going, and so on and so on and so on. And then what we want to do is we remove 12, right? We remove that smallest value. Here it's a leaf, so we can just remove it. And then we remove 8 and move 12 into that location. So basically we remove 8 and move 12 up there. Because we took the smallest value in this subtree, right? We know, because of the properties of binary search trees, that anything over here is bigger than anything over there. And the smallest thing in this subtree is smaller than the root, right? Because we recursed to the left. We always recurse to the left. So we can put it up above and make it the right child. And we're perfectly fine. Right? And this is the tree we end up with. So again, reviewing the removing algorithm, right? This isn't code, it's just an algorithm. We're going to first find the node that we want to remove using our normal search method that we had before, and then do one of 3 things. First is, if it's a leaf, we just remove it. If it only has one child, we sort of replace it with its child node, right? And if it has 2 children, we look in the right subtree for the smallest value and swap it and remove, right? Again, that node, so here we were lucky in that, here we were lucky in that 12 was a leaf, right? But if 12 had had 2 children, well, if it had had 2 children, we would have traversed left further. So it couldn't have had 2 children. It would have only ever had 1 child. So we might have to, when we move 12 up, we might have had to move its child up, right? So imagine it had had 13 still on it, like at the beginning of the video, right? In that case, when we move 12 up, we basically, then move 13 here. Right. Okay, so that's the removal procedure from a binary tree. And again, we'll go over implementation of this during the class period on Monday.